So in this clip, we're going to look at how to find the block diagonal form corresponding to an operator. And so we've taken this operator right here. So this is the one with outputs 6z1 plus 3z2 plus 4z3 and 6z2 plus 2z3 and 7z3. Okay, so in the standard basis, whoops, that was a pretty funky amp. The matrix for this transformation would look like 6, 3, 4, 6, 2, 7. So the spectrum of this operator, then, we can tell by looking at the triangular form of it, is 6, 6, 7. And if we look at t minus 6i applied to z1, z2, z3, that's equal to, let's see, so that's 3z2 plus 4z3, 2z3, z3. So now if that's equal to 0, that can only happen if and only if, well, let's see, from this part right here, we're going to need to have z3 equal to 0. And if z3 is equal to 0, then that means that this part here is going to be 0 as well, which tells us that z2 has to be 0. The only thing we don't have a condition on is z1. So the first coordinate can be whatever it wants to be. So we'll just take v1 to be 1, 0, 0. So there's our first eigenvector. And then to look for generalized eigenvectors, we say, oh, well, what about if we have t minus 6i z equal to v1? So then we're looking at 3z2 plus 4z3, 2z3, z3 equals 1, 0, 0. Okay, so now, again, this can only happen if and only if we've got z3 equals 0 by looking at the last coordinates. But then, in order to make the 1 there, we're going to take z2 to be equal to 1/3. Okay, so then we can take our second vector to be 1, 1, 0. And now we just need something which is linearly independent from the first one. So we could do as the book does and take 0, 1, 0. But I'm going to stick with 1, 1, 0 just so you can see how it works out. And then you'll see that back again in when we continue this example in the next section. So now if I look at t minus 7 identity applied to z, then this is going to be minus z1 plus 3 z2 plus 4 z3 minus z2 plus 2z3 and 0. Okay, and so then this is going to be equal to 0, and I should have left myself slightly more room. There we go. If and only if, and so what do we need? So from this second coordinate right here, we're going to have z2 equals 2z3. And then from the first coordinate, we have z1 is equal to 3z2 plus 4z3. So let's see. So if we take z3 to be equal to 1, for example, then the first equation is going to tell us that z2 is equal to 2. And then putting both of these into the third equation, we get z1 is equal to 10. So we can take our v3 vector to be 10, 2, 1. Okay, so now my generalized eigenspace for lambda equals 6 is going to be the span of 1, 0, 0, 1, 1, 0. And my generalized eigenspace for lambda equals 7 is going to be the span of 10, 2, 1. And in this basis, T1, 0, 0 is going to be 6, 0, 0, which is 6 times V1. And if I do T applied to my next basis vector, then this is 9, 6, 0, which is 3V1 plus 6V2. And if I do T applied to my third basis vector, 10, 2, 1, then this gives me 70, 14, 7, which is 7 times V3. And so taking this data to recover what the matrix looks like in this basis, let's see, so the first column is 6, 0, 0, and the next column is 3, 6, 0, and the last column is 0, 0, 7. And so there we have the block diagonal decomposition that's promised by the theorem. So here's the blue zones of zeros, just to aid with visual parsing. And there you go.